Okay, FTLI 7. All right, again, so problem. What does this thing look like? So C is the boundary of a surface. Let's draw the surface. And drawing the surface is going to be a little hard because it's given in this weird way. So Z equals e to the negative x squared. Well, there's no y's. So what I've got here, I'm going to just draw it in the xz plane, and then we'll just drag it parallel to the y-axis when we're done. So z equals e to the negative x squared is something that looks kind of like this in the xz plane. And then when we drag that parallel to the y-axis, it's like there's sort of a bump sort of thing up here. Like that. Yeah? Everybody good? Okay, and then it, of course, goes over on the other side also. Okay, there you go. So, surface. All right, how does this intersect the unit ball? Well, the unit ball is going to, oh my gosh, well, it's right around in here, right? And so most of the surface is, like this part of the surface isn't part of it. We're just going to be looking at a part of this surface that fits in the unit ball. So it's going to be a little hard to draw, for one thing, but not terribly bad. And it's going to turn out I don't even have to be too terribly precise about it. Let's see. So let's see. What am I going to do with this? Claim it's going to be some little bit of surface. I don't know, something like that, and it's going to come down on the other side some way. Whatever. It's some surface like that. It's terrible. Worst art I've ever drawn, right? But it's a bit of surface. The curve we're interested in is the boundary of this. And one thing that's kind of neato about boundary curves is they always link up, right? They start and end at the same point. What do you think? Does that sound reasonable? I mean, it's just kind of a, we're going to talk about this more actually later in the course, by the way, but I mean, you can't have a boundary that just stops somewhere because then it's not, I mean, if you've got a closed-in fenced region, the fence can't just stop out in the middle of nowhere, and then you're not fencing anything in. I mean, it's geometrically pretty satisfying. Okay, so now we're doing a line integral of a vector field. Okay, let's look at our vector field. What is that? I'm keeping my fingers crossed. I almost feel like it has to be a gradient of something. And let's hope that that works out. Let's see, 2xy, x squared plus 2yz, and y squared. Okay, so that means that my function, whatever it is, has to equal to x squared y plus some unknown function of y and z. It has to be x squared y plus y squared z plus some unknown function of x and z, and it has to be y squared z plus some perhaps unknown function of x and y. So there's our mix and match game. There's an easy winner. X squared y plus y squared z works, right? It's triple check on all three of these. Cool? Everybody happy? So we've got an anti-gradient, and we've got a curve that starts and ends at the same point. So I'm going to just call that point A, and it's all, I guess you could call it B also. It's both the start and end of our curve. So when you do the fundamental theorem line integrals here, the line integral around that boundary of f dot dx, well, it's f of b minus f of a. Those are the same point, so this and that are equal, and so you get 0. Isn't that cool?
Is it the same for the one above, number 6?
Let's see, I don't remember.
Even if it's piecewise, it starts and ends at.
It's the same vector field, so the vector field's a gradient against piecewise straight path that starts at the origin and then goes back to the origin. So yeah, absolutely. Same deal for number 6.
Is that a general rule?
It is, in fact, a general rule. As long as you got to say certain magic words about the vector field has to be continuous, and yeah, absolutely. And if yeah, exactly. So if the vector field is a gradient, and if the curve is a closed curve, if it starts and ends at the same point, then absolutely. Line intervals always 0. I'm going to say more about this actually later. This fact, this particular little coincidence that hey, it's always 0 whenever. 2 things have to work out though. It's got to be a gradient field, and it's got to be a closed path. But if both of those things happen, then yeah, line interval is 0. And there's a similar fact about flux integrals that we'll talk about again later on. It's going to take me a certain amount of time to get to that point. Yeah, question?
So is that still true if you can't find any anti-gradient?
No, it's absolutely not. If your vector field is not a gradient, then it is certainly not true. And in fact, it's not hard to come up with examples. I might even have some examples in the exercises here.
The last time when you're going to get an
Yeah, maybe so. Off the top of my head, let's see here. Well, maybe I can. Yeah, no, that's right. This is not a gradient, and so the answer to this is you can't just assert that it's 0, and I think it's probably not 0.
So then you have to use chapter 5.
Yeah, that's right. This one you might just have to use chapter 5 techniques, and that's, by the way, there's a general fact there that sometimes the fundamental theorem of line integrals just doesn't work out, right? And sometimes, we're later in the course now. We've seen Stokes's curl theorem. Stokes's curl theorem might not apply to this. Actually, let's see, it probably does. C is the curve in the plane. You could try Stokes's curl theorem on that. We're not checked out on that at this point in the course. But yeah, at this point in the course, you've got to go back to chapter 5 techniques. And so I think the reason I put this in the section on fundamental theorem of line integrals is to make sure that students realize that does happen. Tragically, that sometimes you just have to do it by brute force. Now, these boundary theorems, as great as they are, they just are not complete solutions to the problem. Right? Okay, so we kind of talked about 3 problems there. I'm just going to call this one all 3 of those.